When collecting and analyzing data for the comparison of two populations, it is important to pay special attention to the experimental design. This term refers to the manner in which the data is collected. In this section, a distinction is going to be made between paired samples and independent samples. We will introduce an analysis method suitable for when there is only one set of N individuals or experimental objects, and you are making two observations on each, resulting in a sort of natural pairing of values. The advantage of these paired samples is that they can alleviate the effect of variabilities in a factor other than the difference between the two populations. Consider, for example, a new drug for inducing a temporary reduction in a patient's heart rate is to be compared with a standard drug. The drugs are to be administered to a patient at rest, and the percentage reduction in the heart rate is to be measured after 5 minutes. Since the drug efficacy is expected to depend heavily on the particular patient involved, a paired experiment is run whereby each of 40 patients is administered one drug on one day and the other drug on the following day. The spacing of the two experiments over 2 days ensures that there is no carryover effect since the drugs are only temporarily effective. Nevertheless, the order in which the two drugs are administered is decided in a random manner so that one patient has the standard drug followed by the new drug, and the other patient has the new drug followed by the standard drug. The comparison between the two drugs is based on the differences for each patient in the percentage heart rate reductions achieved by the two drugs. Notice our paired samples in this case are in the form of x sub 1, y sub 1, so on, and x sub n, y sub n. This pairing arises from the fact that each N experimental subjects is being subjected to both treatments X and treatment Y. The comparison between the two treatments is then based on their pairwise differences. Notice that with the paired samples, the sample sizes have to be equal, meaning you have to have the same number of X observations as Y observations, since X and Y are needed to make a pair. Conducting an experiment in a paired manner, when it is possible to do so, is a specific example of a more general experimental design concept known as blocking. In this, you are trying to block unwanted sources of variation that otherwise might cloud the comparison of real interest. For example, if the new treatment appears to be better than the standard treatment, could it be because the new treatment happens to be administered to patients who are more receptive to the drug treatment somehow? In statistical terms, the variability in the patients creates more noisy data, which makes it more difficult to detect the difference in the efficacies of the two drugs. A paired experiment, considering the differences in the two measurements for each patient, neutralizes this variability among the patients. Thus, the paired experiment is more efficient in that it provides more information for the given amount of data collected. Because of this reduced variance, it is easier to detect a difference with paired samples than with independent samples. We can now consider when pairing is advisable. If there is a great heterogeneity between experimental units along with a large correlation, meaning a large positive row, then the loss in degrees of freedom will be compensated by the increased precision associated with pairing. So a paired experiment is preferable to an independent samples experiment. However, if the experimental units are relatively homogeneous and the correlation within pairs is not large, meaning that rho is small, the gain in precision due to pairing will be outweighed by the decrease in degrees of freedom. So an independent samples experiment should be used. Antipsychotic drugs are widely prescribed for conditions such as schizophrenia and bipolar disease. The article, Cardiometabolic Risk of Second-Generation Antipsychotic Medications During First-Time Use in Children and Adolescents, in the Journal of the American Medical Association in 2009, reported on body composition and metabolic changes for individuals who had taken various antipsychotic drugs for short periods of time. The sample of 41 individuals who had taken aripiprazole had a mean change in total cholesterol in milligrams per deciliter of 3.75, and the estimated standard error was 3.878. We want to calculate a confidence interval with confidence level approximately 95% for the true average increase in total cholesterol under these circumstances. So what we do here, we would start by understanding that what we're looking for is that mu sub D. Okay, and we can denote that as being, we know that that's going to be the true mean change in cholesterol under the aripiprazole regimen. Now, a 95% confidence interval for this mu sub D, using basically the large sample method, this is going to be, and this is straight from the formula, but we're going to have our D bar plus or minus, and now what we want to do is we're going to calculate our standard score, which is Z sub alpha divided by 2. So when we look here, the first thing we want to do is we have, this is our sample. We have our size is going to be 41. We have our D bar. I have our D bar listed here as 3.75, and then this SD error is the 3.878. So this is what we have. Now we were looking for an alpha of 0.5, which calculates to a confidence interval of 1 minus alpha %, and that's where I get the 95% from. So then we're looking at, what else do I need? I need a Z sub alpha divided by 2. Here I calculate that. And the way I calculate that is using my norms inverse. And I get 1.96. And from there, I can calculate the confidence level. And so here, the confidence level is going to be 7.601. Now, I want this confidence level, of course, to be in absolute terms because I'm going to add it and then subtract it. I'll do that myself. Okay, so I use the absolute value to give me the level because it's an absolute level. So then it's very simple now. I'm going to go in, I'm going to calculate my upper. And for my upper, that's going to be my mean or my D bar, which is 3.75. And then it's going to be plus. And what I get now is I get, for my upper, I get 11.35. And then for my lower, it's going to be D bar minus, right? And it's going to be minus my Z score, which is 1.96 times my SD error. And that's going to give me a negative 3.85. Now, the article also reported that for a sample of 36 individuals who had taken this quetiapine, some other kind of drug, the sample mean cholesterol level change and estimated standard error were 9.05 and 4.256 respectively. Now remember, in this type of analysis, what we're looking for is change. It's the change quantifiable, it's the change statistically significant. And so making, in this case, any necessary assumptions about the distribution of change in cholesterol levels, we want to know, does the choice of significance level impact any conclusions that we might make as to whether or not the true average cholesterol level increases? Okay. And so in this case now, we know that that is cluing us into doing a hypothesis test, right? That right there is telling us that we need to do a hypothesis test. So let's take a look. So the first thing I'm going to do is let's go ahead and define the parameter. And this we do this the same way, step by step. Let's go ahead and define the parameter of interest here. And in this case, it is mu sub d, which is, we want to know the true mean change in total cholesterol levels. That's the parameter that we're interested in. Is there any true mean change in cholesterol levels? And so that prompts us to our hypothesis. So we hypothesize that there is no true mean change in cholesterol levels. So then this is saying that mu sub d is equal to 0. There is no change, right? And so that tells me that my delta naught is going to be 0. We're going to use that, of course, later. All right. My alternate hypothesis is that there is positive change. There is some change in cholesterol levels. And so that tells me that mu sub d is going to be greater than delta naught here. And that's my number 3. So do you see how you can go through and how these things kind of set up? It's very straightforward. And that's why it's good to do the step by step. And it's good to actually put sentences here in your spreadsheet or in your analysis, wherever you're doing it, on your paper, whatever, so that you keep track of what it is that you're doing. So when you get your result back, whether that's to reject or not to reject, you know exactly what it is that you're talking about. So the next thing we want to do is go ahead and compute our statistic. And what statistic do we want to use here? Well, this is going to be a t-statistic, right? Because we're doing paired analysis here. So we want to do this t-statistic. And the first thing I want to do is I want to look, and this is just my rubric. I always like to calculate the numerator and then calculate the denominator and then find the statistic because it reduces error, in my opinion. So what I'm going to do now is I'm going to go ahead and do the numerator. So that's going to be my d bar minus delta naught, and delta naught was 0, so d bar is simply 9.05. Next thing I'm going to do is I'm going to do my denominator. My denominator here is going to be the absolute error, right? It's going to be the magnitude of my error, and that was given, and I already have it as 4.256. And so now I can calculate my t-statistic as 2.126. Well, now that I have my t-statistic, the only thing left for me to do now is to calculate my p-value. And so in this way, when I calculate my p-value, I know that I'm going to need for the t distribution, I know that I'm going to need the degrees of freedom. And the degrees of freedom is always n minus 1. So I know my degrees of freedom in my t-stat is going to be 35. And so I calculate in my t-stat, I'm going to take this number here, which is my 2.126 as the point that I'm evaluating. And then I'm going to calculate this distribution. And Excel has this really neat thing when you're doing the right tail. So you don't have to do the 1 minus the left tail or whatever. It has this, at least in newer versions of Excel, but in my version, it has the t.dist.rt, which stands for right tail. I can use that formula, and I'm taking that for 2.126, and I'm using 35 degrees of freedom. And what I end up with is this here, this 0.020. And so now, clearly, we can conclude that, our conclusion depends on our significance level, and we can say that at alpha equals 0.05, there is evidence that the true mean change in total cholesterol under the quetiapine regimen is positive. But look at what happens when you draw conclusions at the alpha equals 0.01 level. So this is a very interesting thing. So at the 95% confidence level, we see there is evidence that the true mean change in total cholesterol is positive. But at the 99% level, we see something totally different. So I hope that you were able to kind of walk this along with me. If you have any questions, of course, send them to me. But this is just an example of how you would go about and do this analysis with the concepts of using these paired samples.